Some technical university, and then almost for 7 years he worked as a postdoctoral researcher at different research centers in France and China. And then nowadays he is doing research at Bogazici University, and today he will talk about circularly polarized periodic gravitational wave and Pais-Uhlenbeck oscillator. Okay. I am not sure I can pronounce it correctly.
Well, me neither. So not. Okay. We will see. Thank you very much, Eda, for this introduction. Okay. So sorry, I apologize for this title, because actually, you know, what I promised to you is something different. When Eda asked me to give a talk in these nice research seminars, I was just started to do this research, and actually it is almost finished now, and probably, hopefully, the paper, I will post it to archive a couple of days later. So actually I modified the title. It is now a bit more definite, and I will actually tell you about some correspondence, a definite correspondence between a gravitational wave called the circularly polarized periodic gravitational wave and a higher derivative theory called one-dimensional fourth-order Pais-Uhlenbeck oscillator. So I can start if you want, but by the way, you can, of course, anytime you can stop and ask me questions, and if sometimes I speak a bit quick, so you can just stop me and alert me about this. Now I start, okay? So let's say, so the scope of the talk is actually, first of all, in the first section, I will give you a definition of a four-dimensional circularly polarized periodic gravitational wave, okay? So, and I will actually discuss for us, for the scope of this talk, the most important thing is that the symmetry properties of this gravitational space-time. As I told you, it is a four-dimensional gravitational space-time. It is a definite metric, and I will give you actually. And this circularly polarized periodic gravitational wave is belongs to a larger class called plane gravitational waves. And plane gravitational waves, actually, they are a sub-branch of a more general waves or space-times called the PP waves. Therefore, actually, when I started to build this presentation, I started with the PP waves and some of their properties. Then I will be a bit more specific, go to the plane waves, and then lastly I will give you the definition of this particular circularly polarized periodic gravitational wave space-time, okay? And for us, the most important thing, as I told you, the symmetries of this space-time, because as you know from Noether's theorem, a symmetry of the space-time will give you a conserved quantity for the geodesic motion in this gravitational wave space-time. So for instance, let's consider a test particle, a spinless test particle moving in this gravitational space-time. Then each symmetry of the space-time will yield a conserved quantity for the geodesic motion, right? And for us, this is the most important thing. And secondly, in the second part, actually, I will talk about a framework called the Barkman framework, which gives a relation between a PP wave, but mostly we will be discussing a particular PP wave, as I told you, the circularly polarized periodic gravitational wave. So I will give you some kind of a relation, a correspondence between this circularly polarized gravitational wave and a non-relativistic motion, which can be embedded to this gravitational wave. So namely Barkman framework, let's be a bit more specific. So let's consider a four-dimensional gravitational wave. This Barkman framework gives you, for instance, let's take a n-dimensional non-relativistic system, okay? And then you can embed this narrative system, okay, if it is suitable, of course, if it satisfies some of the stuff, then you can actually embed this narrativistic system to a higher dimensional n+2 dimensional gravitational spacetime by using this Bachmann framework, or it is sometimes called Eisenhardt dual lift. So you lift the narrativistic system and it becomes a null geodesic in this higher dimensional gravitational wave. So the crucial point is that some part of the geodesic motion of this test particle in the higher dimensional periodic gravitational wave will be exactly the same as non-relativistic motions. Therefore, it is actually this Bachmann framework is very, very nice, because while you are trying to solve the geodesic equation of motion, you do two things at the same time. You are actually solving the geodesic motion of this underlying non-relativistic system. And since these symmetry properties of these plane waves are very well known, if you lift the system, non-relativistic system, you can investigate the symmetries of the non-relativistic system at the same time. So this is very useful. But in this talk, I will do the opposite thing, so the dual thing. By using the symmetries of this higher dimensional gravitational spacetime, I will derive conserved quantities for the associated lower dimensional non-relativistic system. And particularly for the circularly polarized gravitational wave, I will show that the underlying non-relativistic system is a higher derivative theory called the one-dimensional fourth-order Pais-Uhlenbeck oscillator. Then in the third section, I will derive conserved charges for this non-relativistic one-dimensional system using the symmetries of the four-dimensional circularly polarized periodic gravitational wave. And this is the whole point of the talk, okay? So the rest is, okay, I will give you some, then there will be some discussion, okay? So please stop me whenever you would like to ask any question. I will be happy to discuss. As I told you, this research is, I have been doing it for some time, and I would be very happy if there's some feedback before making it apparent to the public, okay? Let's start with the PP waves. So as you see, this PP wave, this equation 1 is the PP wave metric. Here in Brinkmann coordinates, I will use the Brinkmann coordinate system, where this I goes to 1 and 2. So this x1 and x2 are plane coordinates, and this u and v are light cone coordinates. So without this h is called the profile of the PP wave. If h is equal to 0, then you see this metric is just the flat Minkowski spacetime. Okay, so that means the important properties of the PP wave is captured by this profile of the wave. And you see immediately that the profile H depends only on U and Xi. So it doesn't depend on V. Therefore, you immediately see that there is a killing vector, a symmetry, Xi, which is equal to V translations, right? Del V, which makes the V translations actually, this is invariant, because if you just say that shift the vector V with a constant V plus A, this line element is actually invariant. So it is a symmetry of the spacetime. Therefore, it will give you a conserved quantity, right? Definitely. So, okay, this PP waves actually, they are used for the models for gravitational radiation, just like electromagnetic radiation in flat spacetime. These are actually models for gravitational radiation with the speed of light in the curved spacetime. But I will not be dealing with this, gravitational issues now. What is more important for us is the symmetries of these PP waves, right? And if this PP wave is non-conformally flat, because if it is conformally flat or it is flat, then we know that it is trivial. We know its algebra, it is 042. So it is 15-dimensional symmetry algebra if it is conformally flat, but this is trivial. So if it is non-conformally flat, the symmetry algebra of this PP wave can be as most 7-dimensional. Okay, by symmetry algebra, I say that the killing vectors, for instance, the isometries of this wave, or homothetic vectors, or conformal killing vectors. So the total number of them can be at most 7. And we know actually one of them is Xi, which is the retranslation. This is one of them, of course. So depending on the profile, if it is too much symmetric, then you may have at most, you may have 7-dimensional conformal algebra. Nice. And if this H satisfies this 2-dimensional Laplace equation here, then it is a vacuum solution of Einstein's field equations. Okay, very good. And as I told you, important thing is that the isometries of the space-time, the symmetries and conformal symmetries, they all yield conserved quantities for this null geodesics in this gravitational wave space-time. Okay, so this is the crucial point for us. Now, as long as you consider PP waves, this is the end of the story. Let's try to be a bit more specific and consider plane gravitational waves where this profile is quadratic in X. So it is again a PP wave, but it is a, a bit more specific profile here. It's quadratic in X. Now, as you see, this 2x2 K matrix determines the physical properties of this plane gravitational waves. And the vacuum condition here, which is written in terms of the Laplace equation for the H, it becomes a trace condition for K. If K is traceless, then the Ricci tensor is vanishing, and it is a vacuum solution of Einstein's equations, right? And in that case, if Kij is traceless, we call this space-time as an exact plane gravitational wave. Okay, so this is exact. It is not an approximate solution of, so it is an exact plane gravitational wave. And what else is that for us? The symmetries are important. It is known that this plane gravitational wave, now, no matter it is a vacuum solution or not, it is endowed with a 5-parameter isometry group called the 2 + 1-dimensional Carroll group with broken rotations. Here is the killing vector. So don't worry about, it looks a bit complicated in this Brinkmann coordinates. In other coordinate systems, actually, for instance, in BGI coordinates, it is a bit more simple. So for us, the actual killing vector is not important. The important thing is that we know the symmetries. So here you see this is del over del V, our good old friend Xi. This is V translations are again is a symmetry, of course. This H is a constant parameter. So there's Ci. Remember, I goes to 1 and 2, and there are 2 symmetries here. Okay, these are called Carroll translations. And again, this is Bi, so I goes to 1 and 2. So there are 2 more transformations, isometries. These are called as Carroll boosts. Okay, so in total, 1, 2, 2, so it is 5 symmetries that we are talking about. Okay, here the important ingredient is this L matrix. It is a 2x2 matrix, and it satisfies a differential equation called the Sturm-Liouville equation. And you can see this is this Sturm-Liouville equation. So the second derivative of L with respect to U will be equal to K times L. Okay, so this is a second order matrix coupled differential equation. And you see that for each profile K, you need to solve this equation in order to express explicitly the symmetries of this plane gravitational wave. And I would like to tell that this is a very, very difficult problem. And normally there are not too many analytic solutions. And today I will show you that one of the examples, rare examples, that you can actually find an analytic solution for it. So, okay, this is the profile of the wave K. So each profile you need to solve this equation. There is a secondary condition. L should satisfy this property. So transpose of L is multiplied with the derivative of L should be equal to the derivative of the transpose of L multiplied by L. Okay, and so this solution of this equation should also satisfy this condition. Very nice. And this is the L. Okay, and there's another matrix, a 2x2 matrix called the Suryo matrix, which is actually the integral of the inverse of L transpose L. Okay, So if you are able to solve this Sturm-Liouville problem for a definite plane wave, then you are able to write the symmetry vector, and from the symmetry vector of these isometries, you can generate conserved quantities for the geodesic motion, right? So it is very crucial that you need to solve this equation, but it is a difficult problem that I warn you. Now, what about this Carol? I mean,
sorry, Mahmoud, for interrupting. I want to, sorry for coming back to last 2 slides. I want just, if you can, if there is some mathematical structure that is, that represents what you are working with. What's the geometrical structure? I mean, if there is some mathematical vocabulary that you can maybe comment, because there are some mathematicians here, so I don't know if there is some mathematics. For example, for what's the geometrical structure? Is there some vocabulary, some mathematical vocabulary to the other than?
Well, I think so. I don't know what you mean by vocabulary, but this is a space-time, right? I think it is by geometry. Okay. So what I am trying to tell is that here this is the space-time, and now what you would like to actually.
So space-time, I can represent it as some 4-dimension manifold.
Yes, exactly. Okay. It is a 4-dimensional. Oh, okay. So it is a 4-dimensional manifold. It's a curved manifold. Okay.
Yeah, I mean just to comment with some mathematical language, if you can. So.
Okay, but I So this is a manifold, definitely. And now, I mean, if you would like to, and the symmetries of this manifold, because this is the infinitesimal line element, right? So you would like to actually determine the geodesic motion, which is this, how to tell this? This is in mathematics it's called a curve. So you would like to find the geodesics, the motion of a particle in this background, okay? And any symmetry of this manifold or this space-time, actually by Noether's theorem, will give a conserved quantity for the geodesic motion. And it is very important to, to generate these conserved quantities, because then they really help you to integrate the geodesic equations of motion. Because as I told you, I mean, later we will see the geodesic equation of motion will also give you a Sturm-Liouville equation, which is very hard. So if you are able to generate some conserved quantities, then geodesic motion can be actually very easily, integrated, and you are able to solve your system. So therefore, it is I don't know what to say more, but as I told
you, it's already enough. So thank you.
Enough? Okay, no, you can.
Okay, you can carry on. Sorry for interruption.
No. I mean, so you can just ask anything. I don't know whether I can reply because, as I told you, I'm not a mathematician. I don't know mathematics very well.
Yeah.
But okay, we can discuss. Yes,
already enough.
This is a manifold, definitely. So this is a 4-dimensional manifold. Okay.
Thank you.
Okay. Now, okay, this is a Carol group, and this is just a small slide that I would like to tell you that you maybe you know it probably. The flat-Minkowski space-time has 10 symmetries, and the symmetry group is the Poincare group. You know that there are 4 translations. 3 of them are spatial. 1 of them is temporal translation, and you have 3 rotations in 4 dimensions, and 3 Lorentz boosts. So there is a standard contraction of Poincare algebra. If you take C goes to infinity, then you end up with Galilean transformations, which again have 10 parameters. But the action of the boosts are very different. This is the Galilean boosts. Okay, so some time ago, Jean-Marie Leblanc in 65, he did another thing, an alternative, contraction. If you take C goes to 0, then you can again make a contraction of Poincare group, and you end up with Carol group. In 1 dimension, for instance, this Carol boost. So everything is almost the same with Galilean, except the boost action. So the Carol boosts are somewhat dual to Galilean boosts. But you see, instead of this, so there are no boosts in x in the coordinates, but there is a boost in the time. So therefore, it is a strange kind of a transformations. It defines a strange kind of a metric. Okay, it is a de Genere metric, and it is very interesting. There are a lot of works in Carroll. Here, we are not working in a Carroll manifold. It is not a Carroll spacetime, but interestingly, the symmetries of this four-dimensional spacetime called the plane gravitational waves span the Carroll algebra. Okay, and this is four-dimensional, but this is the algebra of this killing vectors is 2 + 1 dimensional Carroll algebra with broken rotations. So we are not working in a Carroll manifold, but somehow the symmetry algebra of these killing vectors, if you just take their commutators, it will give you exactly the Carroll algebra. Okay, and this is important. Now let's come to the point. Now let's think a test particle, a spinless test particle, moving in this plane gravitational wave. And how do you describe the dynamics? You write a Lagrangian for it, right? And I will give you, and I will write actually this geodesic Lagrangian, which is second order in velocities. So it is not reparameterization invariant. It is only valid for an affine parameter. Okay, and so this is so the x dot means the derivation with respect to an affine parameter, call it lambda. This is our Lagrangian. Okay, if you have this Lagrangian, then you can derive Euler Lagrange equations very easily. So as it is a four-dimensional manifold, we have four coordinates, right? And these Brinkmann coordinates they are global. So okay, so first, for instance, so we have x1, x2, u and v coordinates. So the equation of motion for v is not very important for us. It is decoupled, so I will not present it here. So the u equation is very nice. It is just u double dot, the second derivative of u with respect to lambda is equal to 0, which means that you can take u as an affine parameter. And the equation of motion for x, so the second order, of course, so d square x, d square x divided by d lambda square is equal to k times x. Okay, this is an equation. Looks like a harmonic oscillator equation. Okay. So if you choose u as an affine parameter itself, then the equation for the x turns out to be exactly a Sturm-Liouville equation. It is very similar to the equation that we discussed here for this L matrix. So actually, indeed, these equations are related. If you are able to solve one of the equations, you can solve the other one automatically. And this prime means actually d over du, okay? So at the end, what you get is that, so the way equation, as I told you, not important. If you're able to solve equation 12, which is the equation of motion for the plane coordinates x1 and x2, then you are able to solve the geodesic motion. You can plug your solutions to the V equation, which I didn't present here, and then solve it. So the most important point is solve this equation 12. Then you are done with geodesic equations. But as I told you, it is a difficult equation because for each profile, which may depend on u, it is a coupled equation, and the solutions are not easy to find. Now, okay, let's come to the conserved quantities for this geodesics, okay? So as I told you now, it is a second order Lagrangian. It is not reparameterization invariant. Therefore, you can just easily construct the Hamiltonian by a Legendre transformation. So this is your Hamiltonian, which describes your phase space. Okay, it is in your phase space. So in order to describe this Hamiltonian, what do you need? You need to write the velocities here in terms of coordinates and the canonical momenta, right? And the canonical momenta from the Lagrangian you can derive very easily. These are canonical momenta, and this is your Hamiltonian. Sorry. Okay. So this is your Hamiltonian, and okay. Now the thing is that, as I told you previously, the thing is that actually now you have symmetries, right? For each symmetry, now you will have a conserved quantity for this particle, this test particle, spinless test particle moving in this background. And how do you get them? You just replace this the basis for the vector fields with the associated momenta. Therefore, you can easily write the conserved quantities in the phase space by just replacing this basis like del over del v or del over del x with the associated momenta here, and you end up with conserved quantities for this geodesic motion. Okay, and of course, this, as they are conserved, so they are actually the Poisson bracket of these conserved charges with the Hamiltonian is vanishing actually, and the algebra of these charges exactly gives you the Carroll algebra. Okay, so for instance, these are the Carroll translations and these are Carroll boosts. If you take the Poisson bracket of these translations and boosts, you end up with V translations. Okay, and this is the Carroll algebra. So far, actually, if you have any questions, I can, because now I think we will now work out a definite profile, and I will continue. So do you hear me, by the way?
Yes.
Yes, we hear you.
Very good.
I'm wondering, maybe I missed what you said, but Kij, what does it represents?
Okay, very nice. Okay, Kij is, you see now, if you start with a plane wave, Eda, so you have this edge, right? This is the profile of the wave. So this is because without this profile, it is just flat Minkowski space-time. So this is edge defines the PP wave space-time, okay? This is your profile. Now, let's take a particular class of PP waves, which is where this edge is quadratic in X. Here, it is quadratic, right? And the remaining of the profile is just, this Kij. So this Kij is a part of the metric, okay? And it determines your the physics actually, more or less. So this is so it is a part of your metric, this Kij. An important point is that this Kij is actually here sets, and
it makes the important difference.
Yeah. This is actually the only the only thing that we don't know about it. So this is exactly defines the profile. So this is actually, it describes for instance, you see, if you are able to, so given that Kij, it is a 2x2 matrix, then you are end up with a particular profile. Now I will show you what it is actually for a definite profile. And so, okay, let's move forward. Then I will show you what is Kij. Okay, if you work out with some different example, it will help us. Okay, so but so far, important point is that, so for a plane wave, okay, we know the symmetries, nice, and all these symmetries give you conserved quantities that we have this generic conserved quantities. But of course, for any Kij, for any plane wave spacetime, we need to find these L matrices, which are solutions of a Sturm-Liouville equation, and then we can generate conserved quantities. Okay. Okay, let's work a really very specific example, a particular example, right? Now here, Eda, you see that, okay, let's take a definite Kij here. So let's consider a four-dimensional, circularly polarized periodic gravitational wave, where this Kij is actually, it is a 2x2 matrix. Its elements are periodic functions like cosine and sine. You can see now the elements of this Kij is actually, Kij. K11 is cosine omega u, and K22 is minus cosine omega u, and the off-diagonal elements are sines. Okay, so this is our profile. Now this is our actually metric, a definite circularly polarized periodic gravitational wave. Now you see that here there are two parameters. The first one is the amplitude, which we can take always bigger than 0 or greater than 0. And there's also the frequency of the wave. It is a periodic wave, okay? So there are two parameters that we need to deal with, okay? So they can be anything. I mean, we can take A0 greater than 0, so no problem. And this particular circularly polarized periodic gravitational waves, in the literature, you can see that they can be generated by rapidly rotating neutron stars, or they can be generated in the early inflationary universe. Okay, if you believe, I don't know. For us, it is just a space-time, okay? It is just a metric, a manifold. And okay, and we know that this plane wave, as being a plane wave, it has a 5-dimensional symmetry, okay? This is the Carroll symmetry that we just have seen 1 minute ago. But in addition to Carroll, it is very symmetric. It is an extra isometry called the screw isometry. So it is the screw isometry is a combination of U translations and the planar rotation. This is the rotation, right? This is generated of the rotate, like angular momentum. So, and this is a U translation. So if you combine a U translation with a half angle rotation on the plane, it just leaves, it is Lie derivative action, leaves this metric invariant. So it is a isometry, okay? And there is also a homothetic vector field, which is generic for all plane waves, not only for the circularly polarized periodic gravitational wave, for any Kij profile. There is a homothetic vector field whose Lie derivative action gives you a, ends up with a constant conformal factor here. So if you count the number of the isometries, you have 5 Carroll plus 1 screw isometry, 6 now, and there's a homothetic vector field, it's 7. So, and this is the maximal algebra, right? Because as we discussed, a PP wave can have at most 7 symmetries, and a circularly polarized periodic gravitational wave has this very symmetric structure. So it has 6 isometries plus a homothetic vector field, 7. It's finished now, there is nothing more. So, and this 7-parameter conformal algebra, if you calculate the commutators, you will have this. Okay, the algebra is also, of course, closed, and you can calculate the commutators. Okay, by algebra, we mean the commutators of these vector fields, right? Now, let's go further now. So what we would like to do? We would like to actually solve the geodesic equations. We would like to generate, conserved quantities, right? Now, as you can see, this is the geodesic equation for the transverse part. The U is just trivial. We can choose U as an affine parameter for any plane wave. Of course, this is also true for our particular polarized, circularly polarized periodic gravitational wave. So we need to solve this equation. Okay, good. And the V equation, I didn't present, but if you are able to solve this one, then you can also solve V. So the crucial equation is this one, right? But this equation, if you put everything, and write down the equations, it is a very complicated equation. And the trick to solve is you first switch to rotating coordinates. Here, this R is this SO2 matrix, or the inverse of this SO2 matrix, okay? This is just a rotation, right? And you keep U and V coordinates fixed and just rotate, make a rotation in the plane or on the plane. Then you end up with a new metric. So what I would like to say is that you start with this metric, with this profile, and you make a rotation. It's a coordinate transformation that you can do. And then your circularly polarized periodic gravitational wave metric becomes a new metric. Now, please remember, you had previously A0 and omega. A0 was the amplitude, and omega is actually the frequency of the wave. Now, they combine to give you two new constants on big omega plus and big omega minus. So they are a combination of this omega and A0, okay? The little omega and A0. Now, the good thing is that now this profile part of the wave is actually independent of you. Previously, it depends on you here, but now it is independent of you. Therefore, actually, now the geodesic equations of motion become a bit more simpler. And now you can able to solve the equations. Okay, of course, if you push forward this Carroll vector fields here by this rotation, right? Because you did a coordinate transformation. Now, if you push forward the vector fields in these new rotating coordinates, the Carroll symmetries become this. So this rotation matrix actually, enters into the expression for the symmetries. Nice. And okay, it looks very complicated, but don't worry, we will solve them. They will be very easy later. And now what will we do? We would like to actually, deal with geodesic equation of motion. Okay, we will write again the geodesic Lagrangian, which is second order in velocities. And then from here, we can make a Legendre transformation and go to phase space and write the associated Hamiltonian in these rotating coordinates of this circularly polarized periodic gravitational wave. And that, of course, we can define this canonical momentum. So you can see this, it is a four-dimensional wave, right? Then there are four coordinates. The phase space will be eight-dimensional. So for each coordinate, for instance, for x1, x2, you will have p1, p2. And for v coordinate, you will have a pv, the momenta, canonical momenta. And for u, you will have a pu, another coordinate. So it is a eight-dimensional phase space, right? Nice. And now you can see very easily from this profile, you can see it is symmetric under the v translations. So our friend psi, which is equal to v translated, this del v, is again a symmetry of this space-time. Nice. Therefore, PV is a constant. You can calculate very easily. Now, actually, it is an element of this Carroll. Now, we see that, for instance, as this profile is actually U independent, because if you change U, if you shift U, the coordinate with a constant U plus B, where B is a constant, this profile is again, the line element stays the same. It is left invariant, and therefore Pu is also a constant. Very nice. And so you have all these actually conserved charges, for instance, they commute, Poisson commute with the Hamiltonian, therefore they are conserved, right? Very nice. Now let's make go to other section. Now we actually have everything. Now because we have symmetries, we have conserved quantities, we can write. So what I would like to now tell you that, as in the beginning of the talk, I told you that, okay, this is a four-dimensional manifold, or it's a four-dimensional plane gravitational wave. And now we are dealing with circularly polarized gravitational wave. Okay, very good. It's four-dimensional. So the geodesic motion is also four-dimensional, right? And I told you that actually there is a framework called the Bargmann framework, where you can actually, somehow lift a non-relativistic motion to this gravitational wave and work out its symmetries. So therefore, what I would like to tell is that the Bargmann space, so this four-dimensional PP wave metric, okay, let's be a bit more specific. Let's say that this four-dimensional circularly polarized periodic wave can be viewed as a Bargmann space for a non-relativistic system in lower dimensions, okay? Or you can say the opposite. You can take a non-relativistic motion and lift it Eisenhower to Y. So you can embed it to a higher dimensional PP wave space-time and work out the symmetries there. So how does it happen? Because actually we will see that this geodesic motion here, this has been done Eisenhower 100 years ago. This the non-relativistic motions that we will generate now will satisfy the same geodesic equation. So therefore, actually, you see there's also V equation. So this is four-dimensional geodesics, right? But the V equation is just decoupled. The important part is the equation of motion is for us this x equation. And actually this x equation defines a non-relativistic motion at the same time. And we will see now in a minute on the example. How do we do? Now, let's consider only null geodesics, which means that we are working about our test particle is massless. As you can see, this our test particle is just p square, so p mu, and we constrain it to be massless, which means that it should be equal to 0. Then from this equation here, you can just extract a non-relativistic Hamiltonian. And it will be equal to exactly minus pu. So you see, this is here, what you get here, this non-relativistic Hamiltonian, it has a 4-dimensional phase space, right? Because it is only pi's, so 2 momenta and 2 canonical coordinates. And the important thing is that the u, which was a coordinate for the 4-dimensional space-time, it becomes the Newtonian time for this non-relativistic system. So u should be interpreted as the Newtonian time, the absolute time. And PV, which was a constant for the geodesic motion in 4 dimensions, becomes the non-relativistic mass in the lower dimensions. And if you work out the equations of motion, for instance, for this non-relativistic 4-dimensional phase space, now it is very easy because you just derive the Hamilton equations, and this is the equation of motion, the first order equation of motion for the coordinates, and these are the equation for the momenta. Then if you combine them, you will get second order Euler Lagrange equations for y1 and y2. Okay, and here u is actually time, non-relativistic time. Now, what I would like to tell you, the important point is that these equations, these are non-relativistic equations interpreted, but these equations 33 are exactly the same equations that if you would like to derive equations of motion for the geodesics of this Lagrangian, the equations of motion for y, if you use u as an affine parameter, and you can do it, the equations of motion will be exactly the same as these equations. So these equations you can interpret as non-relativistic equations for a lower dimensional system, or a part of geodesic equations for a higher dimensional gravitational space-time. Therefore, actually, there is a correspondence between a lower dimensional non-relativistic system and a higher dimensional PP wave. So this part is really important. So if you would like to ask any question, what I would like to say is that this is actually the essence of the Eisenhower dual lift. So take some equation of motion. Okay, so take this system, because this defines a system that we will now work out. It is a Hamiltonian here, a non-relativistic Hamiltonian. You can lift this Hamiltonian. It's 2-dimensional. I mean, phase space is 4-dimensional, but the configuration space is 2-dimensional. You can lift it, and it becomes a plane gravitational wave, this metric. Okay, and
sorry. I want to ask something. In the beginning, you said that we have 5 symmetry.
Right.
And then we have 7 symmetry, and yes, it's the maximum limit.
Yes.
Of the symmetry. And okay, my question is, we add this another 2 symmetry. I think one is coming from the isometry. But I missed the other one. We add this because our objection is to going to the higher or lower limits.
No. Look, so there are no limits, first of all. Okay, let's say that this isometry. Okay, but these are not actually, we didn't add anything. So let's say that, okay, it's very important. So any equation is actually very important because it is a complicated, you see, a bit. Now, so if you are working with a plane gravitational wave, okay, with a generic profile Kij. Now, it is known that it has 5, okay, mathematicians also worked it, so you can find it in the literature. So it has a 5-dimensional symmetry, okay? So the isometric group is 5-dimensional. So how do you do this? You just, write the Killing equations. So take an arbitrary Killing vector, write it as action on the space-time. That means the Lie derivative, right? And then you need to solve these equations. And then while solving it by brute force, whatever, you end up with some structured differential equations. And then you see that if you count the number of the freedom, whatever, you will see it is 5. So for a generic profile of a plane gravitational wave, you have 5 symmetries, okay? But depending on this K, if you work with a specific profile, because of the structure of the K, you may have an additional isometry or a conformal symmetry, okay? So this really case dependent. So for us now, we work with a definite profile, okay? Circularly polarized. Now the K is known. It is elements, it's a 2x2 matrix. Elements are cosines and sines, right, Eda?
You choose Kij specifically.
Yeah, definitely. Now I'm working with a definite 4-dimensional circularly polarized periodic gravitational wave.
Okay, in the first place, it's general, and then
yes, exactly. And now for this generic profile, if you would like to work out Killing equations, you see that apart from these 5-dimensional Carroll symmetries, you have an extra isometry. So therefore, it is not addition, it is there already. So once you work out this profile, you work out the space-time, definite space-time, you have, because of this, very symmetric profile, you have an extra symmetry vector. And it is really particular to this Kij, okay? So therefore, it's not an addition by hand. It is just there because your profile is very symmetric, okay? So somehow the U translations normally, Eda, if this Kij is, you see from this metric, you can understand. So you don't know, for instance, the U translations may not give you a symmetry because this Kij can be any function of U, right? Therefore, if you shift U, it may not be symmetric. It may not stay the same. Okay, very good. And you don't know, for instance, because it depends on K, if you just rotate this part, if you make a planar rotation, this metric will not stay the same in general, right? But so in particular, yeah, but for this particular profile, Eda, you can make a U translation, okay? So U goes to U plus A, and then you can rotate your coordinates here, x1 and x2, again, with a half angle omega divided by 2. So and if you do this both in your system, this part will stay the same. You can calculate it. So this symmetry 19, called the screw isometry, is really particular to this particular profile, okay? So therefore, in addition to this 5 Carroll, you have an additional symmetry. But the homothetic vector field is generic for any plane wave. So you can calculate. Well, but the isometries this isometry is really particular. Therefore, it is maximally symmetric. It is a 7-dimensional conformal algebra, definitely. And therefore, actually, because of the screw symmetry, you can just rotate your system. You can rotate your coordinates, x1 and x2. This is the SO2 matrix, right? And then you end up with a U-independent profile here, okay? Very nice. And this is because you have the screw isometry, actually. Without this extra isometry, this trick will not work. And then, okay, then in this, then you have actually these equations of motion for the y's. Okay, is it okay now, Eda? Do we agree on?
Yes, thank you.
Okay. Now the crucial point is that these equations of motion for the non-relativistic system is exactly the same equations of motion for the part of this geodesic motion if you take u as an affine parameter. So you just generate this, you just write down this Lagrangian here by using this metric, derive equations of motion. What you will get is that u double that will be equal to 0. Then you will take u as an affine parameter. And if you do, then the y equations will be exactly the same. But these equations, if you do this null reduction here, you just, from this Messel's condition, you generate a non-relativistic Hamiltonian with a lower dimensional phase space, 4-dimensional phase space. The equations of motion for this Hamiltonian structure is exactly the same. So what I am trying to tell you is that actually the geodesic equations of motion for this 4-dimensional space defines you a lower dimensional, 2-dimensional, let's say, non-relativistic equations at the same time. So therefore, you can see this with the two opposite pictures. So firstly, you can say that my PP wave can be viewed as a Barkman manifold. So I can just, by solving the equations of motion for the geodesics, I can also actually, reduce them. I can project them and I get a non-relativistic system. Or you can say that, okay, I have a non-relativistic system and I can embed it to a higher dimensional manifold. The dynamics are the same because these equations of motion for the non-relativistic system is exactly the same equations of motion here for that one, for that part of the geodesics, 4-dimensional geodesics. So while you are working the geodesics of a 4-dimensional this manifold, you're actually doing at the same time relativistic, non-relativistic physics at the same time. So this is the essence, okay? And this is sometimes very useful because if you have, for instance, a non-relativistic system, and this is the part actually that I will tell you now, you can just, lift it and then work out the symmetries there. It is very useful. Or now I will tell you that the opposite picture, we know all the symmetries, okay? Okay, we have 5 Carol, right? Here. And there's a screw isometry 6, and there is a homotety. I can generate conserved quantities for the 4-dimensional geodesic motion here for the relativistic metric. And all these conserved quantities project to the non-relativistic system here, which is a lower dimensional, right? It is a 4-dimensional phase space, and they will be conserved quantities for this non-relativistic system. Here, you just see that the coordinates, for instance, this u, which was a coordinate for the higher dimensional system, it is interpreted as a Newtonian time. And the PV, which was a conserved momentum, it becomes non-relativistic mass. Therefore, you are just, so this V coordinate is just decoupled, it goes away. U becomes Newtonian time. Therefore, previously you had a 4-dimensional space-time. Now you have a 2-dimensional space-time, but the latter is non-relativistic. So this is the picture, okay? Now, if it is okay, so this equation 33 is an equation of motion for two things. It is an equation of motion for the non-relativistic system, but at the same time, it is a part of the geodesic motion for the 4-dimensional space-time. If you take U, so in the first one, for the non-relativistic system, U is time, the absolute Newtonian time. For the 4-dimensional relativistic motion, this U is a coordinate, but since U double dot is equal to 0, you take U as an affine parameter, and so therefore these equations are invariant for both, for both these relativistic and non-relativistic systems. The equations of motion are the same. Okay, and let's solve them. Okay, but important point is that, which we didn't so far actually worked out. This is the first time. These two equations. How do you get these two equations? You combine these two Hamilton equations, which are first order. You combine them, and you get the second order equations for y1 and y2. Now, the thing that which we discussed previously, I discussed it actually, okay, not important, we don't have too much time. You can actually combine these two equations and you end up with a fourth order equation for each I. So one of them, let's say you can choose one of them, and it becomes a fourth order equation. And this fourth order equation is known as the Pais-Uhlenbeck equation, okay, oscillator equation. So therefore, it is a surprise actually that, so this equation of motion, which is actually two-dimensional, I mean the configuration space, y1 and y2 is two-dimensional, right? Now you combine it, so that means for each equation the second order equation, you have 2 degrees of freedom. In total, you have 4 degrees of freedom. And you can combine those equations. For instance, you can take the derivative of y1 here, the first equation, plug the second derivative y2 to here, and then take the derivative again and then plug it again. You end up with a fourth order equation for, say, y1. And as being a fourth order equation, you have 4 initial constants, right? 4 degrees of freedom. So therefore, the degrees of freedom are the same. And the interesting point is that actually now these equations here, narrative equations, define a higher order theory called the Pais-Uhlenbeck oscillator. Therefore, we can say that, now I will show you definitely, we can say that the narrative system of a circularly polarized periodic gravitational wave, the underlying narrative system for a 4-dimensional circularly polarized periodic gravitational wave is actually a 1-dimensional fourth order Pais-Uhlenbeck oscillator. Okay, but this is just the equation of motion. Let's do this analysis in the Hamiltonian space. These equations, I will be a bit more quick now. I need to probably finish. Okay, these equations here actually can be generated with a symplectic structure, right? It's a Poisson, it's a symplectic manifold now, if the mathematicians like it. So this is your symplectic form. It is a 2 form, it is closed, but it may not be exact. Okay, and this is the Hamiltonian. And this is, of course, the sigma, the symplectic form, gives you the inverse of sigma will give you the Poisson brackets, right? And the equations of motion that you can generate from this symplectic structure will automatically give you these equations of motion. Okay. Now, what you do is that how to solve these equations of motion. This is the point, right? Now, what do you do? These equations of motion are actually U independent, so time independent. The coefficients are time independent. Now, there is a nice method called the chiral decomposition. You just rewrite this sigma, the 2 form, symplectic 2 form, and the Hamiltonian in such a way that, in good coordinates, in such a way they are decoupled. Because here the problem is these equations are coupled, right? If you decouple them, then you can solve them very easily. And if you work out this chiral decomposition, you have new coordinates, let's say x plus 1, x minus 1, x plus 2, x minus 2. You can rewrite the sigma and the narrativistic Hamiltonian and decouple them to plus and minus sectors, okay? So actually, now important point is that here, this sigma is, these are plus sectors and these are minus. And for the Hamiltonian, this is again plus and minus here, you can see. So it's completely decoupled. And then if you just write down the equations of motion for this symplectic structure in these new coordinates, you end up with simple harmonic motions. Very easy. And we know how to solve simple harmonic motion, right? It is just trigonometric functions. And the simple harmonic motions for this big omega plus and big omega minus, right? Therefore, the solutions are very easy because it's a combination of one simple harmonic motion with omega plus and the other simple harmonic motion with omega minus. And you have 4 initial constants, right? To be determined from the initial conditions, say. And this is for y1 and y2 is automatic. And these are the solutions for the narrativistic motion here. And these solutions are actually, they are solutions for the relativistic part of the motion here. You just write down y's, y1 and y2, unrotate them, because here you make a rotation, right? You unrotate them and you end up with the geodesic solutions for this general Brinkmann metric for the y's. Okay, so at the same, so you solve the geodesic equation of motion for both the relativistic system and the relativistic system because they are the same. So very nice. Now the thing is that I don't have too much time here, but I showed that the equations of motion and these solutions actually solve the fourth order Pais-Uhlenbeck oscillator here. Okay, and we have 4 constants of motion because it is very consistent because this is the fourth order equation. Very good. Now the thing is that if you redefine this x plus 1, x plus 2, x minus 1, x minus 2 with new small x and small p's, momenta and the coordinates, and rewrite this symplectic structure again, then you end up with a canonical coordinates because now your symplectic 2 form is just dp dx. This is the regular thing that we know. So we are now working with canonical coordinates. And okay, you see that your Hamiltonian becomes a combination of 2 harmonic motions, but there's a minus sign here. And this is interesting because now you see that normally for such a system, the energy is not positive, definite, right? Because of minus here. And this is a sign for higher order theories, because if you have a higher order Lagrangian, okay, let's say that Newtonian equations of motion actually are second order, right? And oh, okay, Newtonian equations of motion are second order. Therefore, if you make it, if you write the Lagrangian, Lagrangian is quadratic in x prime, the velocities, right? And then you can just write the Hamiltonian, which becomes p squared divided by 2m plus the potential whatever else, right? And because it is p squared, and you can of course set your potential generally, you can set it. It is because it's only the potential difference which is important. So your Hamiltonian is positive definite, right? And if you would like to quantize the theory, that means you have if you have a positive definite Hamiltonian, you have a definite ground state with a minimum energy, right? And so that means actually your Hamiltonian, your spectrum is bounded from below. But here, this is not true because your Hamiltonian is not positive definite. And if you would like to quantize it, it is theory, you will have some problems. But this is another story. But this is, you see that this is a sign that you cannot actually set your potential, and you cannot make this Hamiltonian a positive definite one. And this is a sign for higher derivative theories because due to Ostrogradsky's theorem, actually, if you have a higher derivative Lagrangian, that means your Lagrangian doesn't start with velocities. It may start with accelerations, for instance. And I will show you, it will be this, this is exactly the case. Then you have such a Hamiltonian, which is actually not positive definite. Therefore, we don't use them too much in physics, but they are sometimes really useful. Now, you see that, now these are the equations of motion, Hamiltonian equations of motion, and they define you some simple harmonic oscillators. And there's a final canonical transformation. And then you end up with this Pais-Uhlenbeck oscillator here. Very nice. So after all these canonical transformations that I did for the narrative system, I end up with a Pais-Uhlenbeck Hamiltonian. And I previously showed that actually is Hamiltonian, and also the equations of motion are the same. Therefore, what I conclude was that the Hamiltonian, both the Hamiltonian are, so the narrative system for the CPP gravitational wave actually can be mapped to a Pais-Uhlenbeck oscillator. And now you see that This is linear in momenta, therefore it is not positive definite. So these are all quadratic in coordinates, but there is a term which is actually very generic for any higher order theory. It is linear in momenta and velocity. So therefore it is not positive definite. Okay, there is not, it is nice. And the Lagrangian for this Hamiltonian, you can find out, you see it starts with acceleration. So it is quadratic in acceleration. Therefore, it is a higher order theory. And the equation of motion is automatically it starts with a fourth order derivative. And this is the Pais-Uhlenbeck oscillator that we find previously, right? And the Hamilton analysis is very, very. But you can do here. There is a, as being a higher order theory. There's this X, which is in your configuration space, nice, but you need to define a V, which is our velocity, as an independent coordinate, okay? So as X and V are different coordinates, then there will be associated momenta for each of them. So for X, there will be Px, and for V, there will be PV, okay? So your phase space is four-dimensional, which is exactly the case in our system. Okay, so therefore these are the Hamilton equations. And okay, now I think I don't have to, I already exceed my time, but just I would like to tell you that briefly, maybe in 5 minutes, I would like to tell you the remaining part. So, okay, please remember. So first of all, our circularly polarized periodic gravitational wave, it has a 7-dimensional conformal algebra. So 5 of them are Carroll, 1 of them is Scroll isometry, the other one is homotopy, right? And all these symmetries will give us conserved quantities for null geodesics, right? Very nice in 4 dimensions. Now we can, but this is for relativistic physics. Now we can generate, we know that actually there's an underlying system, non-relativistic 1-dimensional system with a 4-dimensional phase space called the Pais-Uhlenbeck oscillator, right? For our circularly polarized periodic gravitational wave, and the symmetries of the CPP gravitational wave can generate conserved quantities for our 1-dimensional Pais-Uhlenbeck oscillator. Okay, and these conserved quantities we will see they will be explicitly the time dependent. Okay. The idea is, of course, you have symmetries, you will generate conserved quantities in the higher dimensional system, then you project them, and you just push forward all these conserved quantities and generate new conserved quantities for this Pais-Uhlenbeck oscillator. And okay, for the screw charge, for instance, at the end, if you write down in terms of Brinkmann coordinates, it will be Pu plus this thing, okay? And at the end, you project it, and then you will do this coordinate transformations in the phase space. This screw charge, this charge for the screw symmetry of the gravitational wave becomes the Pais-Uhlenbeck Hamiltonian, which is actually time independent, and therefore it is conserved here. So you end up with here. So your screw charge gives you the Pais-Uhlenbeck Hamiltonian. So this is conserved. Now, okay, the homothetic charge, it is a different story. I will just skip it. It gives you actually the real theorem for this Pais-Uhlenbeck system, because as you see, if you just rescale this Pais-Uhlenbeck Lagrangian, x goes to x plus lambda, x times lambda x, the Lagrangian will be just scaled, and Hamiltonian will be 2. Therefore, you will have an integral charge here in terms of the phase space variables. It gives you that. Okay, not important maybe. More important is that the Carroll charges. What will be the fate of Carroll charges? Now you have a Carroll symmetry for the gravitational wave. It will give you conserved quantities for the geodesics in 4 dimensions. Now you can project them. I will not give you all the details, but okay, it is a bit hard stuff. But as I told you, since we solved the geodesic equation of motion, we can solve the Sturm-Liouville equation here. It is a bit difficult but technical. I will just skip the details now. Okay, this is the Sturm-Liouville equation, right? And this is the matrix 2 by 2 equation. But this equation and the geodesic equation are almost the same. But we solve the geodesic equation here. We know the solutions of it, right? It was in terms of this trigonometric functions. Then we can also solve the geodesic equation, the Sturm-Liouville equation for the L matrix here. And if you do this, okay, it is a bit technical. You end up with this Carroll charges for the Pais-Uhlenbeck oscillator. Okay, so this O matrix is just the multiplication of the L matrix with the SO2 matrix. Okay, no problem. We can just use an initial condition of the original four-dimensional problem, and then our O matrix should satisfy these conditions, and now we end up with a very simple O matrix, which is our almost Sturm-Liouville matrix. Okay, and then plugging this into these charges, for which are actually charges coming from the Carroll symmetry of the plane gravitational wave, we end up with these charges for the Pais-Uhlenbeck oscillator. Okay, finally, and this is, you see, these charges are a bit not very complicated. It's just, you know, this is the x of the coordinate of the Pais-Uhlenbeck oscillator. This v is the velocity, and this px is the canonical momentum for x, and pv is canonical momentum for v. And these are Carroll. Previously, they were actually, these are two Carroll translations. The Carroll symmetries, they correspond to the Carroll symmetries of this gravitational wave. And these are the Carroll boosts. They are projected for the non-relativistic system. And then I made some coordinate transformations, okay? And they are conserved in the PU phase space. And okay, they have some interesting, but the algebra is interesting. This Poisson algebra of this whole this stuff actually spans the Newton hook group. So for the gravitational wave, there was a Carroll symmetry. The commutators or the Poisson brackets of these four-dimensional objects, they actually give you a Carroll, the Carroll group. But when you project this group, structure changes, it altered, and it becomes a Newton hook group actually here with a central extension M. So M is just, you may remember, it was a non-relativistic mass, and this is the central object in the algebra. Okay. Okay, and finally I finish. Sorry for this. So what did we do? I just actually showed that the underlying non-relativistic system for a four-dimensional circularly polarized periodic gravitational wave, which is the relativistic system, the underlying non-relativistic system is the one-dimensional Pais-Uhlenbeck oscillator. And then, starting from the symmetries of the gravitational wave, I just derived conserved quantities for this one-dimensional non-relativistic Pais-Uhlenbeck oscillator. It's the fourth order theory, by the way. And okay, and by the way, in the literature, actually there were papers for the symmetries of the Pais-Uhlenbeck oscillator, but they have a very different method, actually, starting from the Newton hook algebra. They were trying to construct, and they can only find the conserved quantities when this omega plus and omega minus have a certain relationship. Here, in our case, we don't need this relationship. We only need omega plus should be greater than omega minus, which is natural in our setting. So therefore, and our charges here, if you choose omega minus or omega plus is 3 omega minus, they are compatible with the ones in the literature, but these are more general than. And okay, there are some other things that, for instance, I can just search. What I did is, first I had the gravitational wave, then I project it to the non-relativistic system, then I do some coordinate transformations, end up with the Pais-Uhlenbeck oscillator. So, and in the literature, actually, people were trying to lift Pais-Uhlenbeck oscillator, and they couldn't do this. Actually, okay, they did it, of course, very nicely, but they didn't end up with a plane gravitational wave. They end up some kind of a bit more complicated profiles. But perhaps it is possible to do all these coordinate transformations at the metric level, and this will certainly give some, maybe some important idea for how to lift these higher derivative theories. And there are some interesting systems which actually are related with these structures. For instance, this CPP gravitational wave is actually a double copy for electromagnetic configuration. Therefore, I am actually a bit curious about these chiral charges, how we can just, push forward the chiral charges for this electromagnetic vortex, which is an electromagnetic configuration. And okay, there are some other things that I can do, but it is better to finish. Okay, right? Maybe it is, I exceeded my time, so sorry for this. Okay. If you have any questions, I would be very happy to.
Thank you, Mahmut, for this nice talk.
Thank you.
We already discussed some parts, but I think we have a few minutes if there is a question. Okay.
Maybe I can just general wondering about because the choice of, so if I understood right, you on the profile KEG, you add some regularity on this profile, and it helps in gaining some symmetry on the matrix.
No, let me say, okay, that so no, this Kij can be anything. Okay. Now I choose a particular Kij. So
Yes.
I didn't add anything actually. So this Kij can be anything. So depending on the Kij, this system may have a different, right?
But at the start you have 5 symmetries, and then the choice.
Yes, definitely.
Yes.
But you see that the symmetries depend on K, right? So for here you see, and this is very.
So the more your choice is smooth or is you have more symmetry. So we can. This is the grand logic of it. I guess.
Yes. For any Kij, this Kij is a 2x2 matrix. It's a U dependent, right? So for any Kij, we have 5 symmetries. Okay, nice. And okay, I need to charge. But for particular Kijs, you may have more symmetries.
Yeah.
Right. And so, this is the stuff actually that we have now.
My question is about the lift that you are making, because you have said that you make a lift to by the lift you reduce 2 dimensions.
Definitely. Actually, you see,
and now, by the choice of KEG, you gain 2 symmetries. I'm just wondering if there is a link between these two.
No. Actually, you see, but now, look. Wow, this is very nice. Okay, really nice. So I think, okay, let me just charge the, okay. So first of all, you see the symmetries that I'm talking about, the chiral symmetries, right? They depend on Kij. So, okay, let me do, it is a very nice, really a nice question. So, okay. Okay, so you see that here the symmetry vector for any Kij is this one, right, Ayman? Now, but this L matrix is actually K dependent. So for each K, you need to solve it. It is different. So this is the generic vector with a generic expression, but for each Kij, the profile, it is different. Therefore, you need to, in order to, write this killing vector, you need to solve this equation for each K, right? And okay, and now I choose one K here, which is called the circular polarized periodic gravitational wave, right? Now, and there are 5 symmetries normally, and this homothetic vector field, it is also generic for the plane wave. So this plane wave actually has 5 symmetries plus 1 homothetic charge. But depending on the structure of the K, it may have 1 more. And for this particular profile here that I work out, it is actually 1 more.
Yeah.
Okay, but this.
But it's dependent on the translation by you.
Exactly,
And
translation
so
by
you
you.
periodize. You periodize in
Exactly,
certain sign. Yeah.
exactly. So this periodic structure actually, if you just shift this cosine and sine, okay, it will not be the same, but you can compensate with a rotation on x here. Then it is this part will be this symmetric. So this is a symmetry vector, really. It is a killing vector. So if you act the Lie derivation of this vector field to this metric, to this with this profile, it will be invariant, right? But the thing is that about this narrative dynamics, it has nothing to do with this particular profile. It is very general. So for any PP wave, okay, here for instance, this is the most general profile. You can do this reduction thanks to this killing vector. Everything comes from this generic killing vector. Okay, in the beginning, a generic PP wave spacetime is defined with this covariantly constant null killing vector. Okay, and therefore you can make a reduction because this profile doesn't depend on V. Then actually you can write down the Lagrangian, geodesic Lagrangian for the spacetime, right? It will be exactly the same that we were writing here. Instead of k, it will be h, right? And it will not be quadratic in x, it will be anything. So instead of this k xx, it will be 1 over 2 h u dot square. Then you can derive the Hamiltonian for this h, the generic profile. It will be exactly the same. Instead of this k xx, it will be h only. Then you can just equate it because now you can say I am working only with massless geodesics, and the massless condition is p squared is equal to 0, right? This is the momentum squared should be equal to the minus m squared. But if m, the relativistic mass or the invariant mass of the relativistic particle, if you say it is equal to 0, I am working with massless particles, then you can equate this Brinkmann-Hamiltonian to 0 for any h. It doesn't depend on k or whatever. So for any h, then you end up with a non-relativistic system. Okay. The problem is this non-relativistic system that you find may not be interesting. So if you can find some interesting system, an underlying interesting system, and discuss its symmetries in a novel way, then it is something, you know, nice. And this happens here, you see. So you can work out any age, and this age actually here, it is a profile of your gravitation or PP wave, right? And for the narrative system, it is your actually, this gives your potential. Okay, so if you have a Hamiltonian, say my Hamiltonian is T kinetic part plus H, you can lift it, and then this H comes, the potential part comes to, and it becomes this profile of the gravitational wave. This is the story actually. So you can make it for any H, and this Kij, Xi, Xj, which is a plane gravitational wave, is a particular class of this PP wave spacetimes. And what we are working here is a definite one. So I just select, you have infinitely many possibilities. I select one of them, which is this circularly polarized periodic gravitational wave. Then your profile is definite because it is just cosine and sines. So Kij is just, you know, it is a matrix of cosine, sine, sine minus cosine, finished. So it is definite, everything is. So you can do this Bartman framework, or you can just project the non-relativistic dynamics for any H, okay? But here, in our case, for this definite system, you can project it and you get an interesting system called the Pais-Uhlenbeck oscillator. Then it is very nice because then we can actually generate conserved quantities in a novel way. And these conserved quantities that are generated are actually novel in a sense that in the literature, they do it very nicely with a different technique, but in their charges, there must be a relation between these omegas. In my case, I don't need any relation because the symmetries. So in their system, for instance, in the literature, this omega plus should be 3 times omega minus. In my case, you don't need such a relation. So you only need that omega plus should be bigger than omega minus. So there must be, this should be omega minus. This should be omega minus. There's a typo here and nothing else. And this is very natural, you see. So the thing is that you have a gravitational wave, you have an underlying narrative system, right? But not all the systems are very interesting. If you are able to find a narrative system, which is interesting, that you can embed to a gravitational wave, and in addition, if you are able to solve the Sturm-Liouville equation here, which allows you to write down the symmetries explicitly and generate conserved quantities and project them, blah, blah, blah. So everything should be in order, right? So all the the planets should be in an order. Then you have a good fate. Then the things will be very good for you in the future. So if you are interested in astrology. So here it is really a happy coincidence that everything can be done. So this is a really integrable system in a sense that we can solve the Sturm-Liouville equation. We can find an interesting narrativistic system for our gravitational wave, a particular one, okay? Not for any. So this is just a particular one here. And then it is very interesting that you can solve everything. And this is actually, we can solve because there's this extra isometry here. But this extra isometry has nothing to do with the this Bartman framework or this lifting. The lifting is actually can be done for any PP wave, okay? Then the potential of your narrative system will be this H. So
okay.
I don't know whether this
so
is
it has nothing to do with the additional symmetry of your particular choice.
Yes, but the additional symmetry allows you to solve this Sturm-Liouville equation. So this is that important because without solving it, you cannot write down the conserved charges, very explicitly, right? Because you need to solve this Sturm-Liouville equation here. Okay, here, for instance, or this one, which is very hard, but thanks to this extra isometry, if you have many symmetries, then the system is integrable, right? And Pais-Uhlenbeck oscillator is really integrable system because you have actually 5 conserved quantities, and it is a 4th order equation. Therefore, it is, I think it is, how to say, super integrable or something. Therefore, you are able to do this. I mean, then with this extra isometry, I can solve the equations of motion. I can solve this Sturm-Liouville equation and write these conserved quantities. You see, they are very simple. Finished. Normally, you cannot do this. I mean, for any profile Kij. Pick one of them. It is not possible generally. But for this one, thanks to this extra isometry, yes, it is possible, and you can find a narrative system which is interesting. Pais-Uhlenbeck oscillator. It is very distant. You see, you have a gravitational wave, and the underlying system becomes a one-dimensional higher order theory. They are very, very different, actually. I mean, not easy to see the relation between them. I only see it by a coincidence. I mean, normally I don't think I can see it really. I mean, it is not apparent actually. That is the whole point.
So it's a question of astrology again.
Yeah, definitely. I mean, so as I thought, this is actually done by Eda. So Eda was saying that, okay, everything is in order now. I mean, all these planets are in an order, they align, then your future is very bright. And here it is the same. I mean, you can solve it, you can solve Sturm-Liouville equation, you can find an interesting narrative system for this definite profile. Well, everything works very well. But for any profile, this will not work. I mean, this is really profile dependent. You see, I mean, there are not too many interesting narrative systems for a gravitational wave. For instance, here, I didn't tell you, but here, if you have another periodic wave called linearly polarized periodic gravitational wave, the corresponding narrativistic systems are ion traps. A very important things that's actually, the ion traps actually, they got Nobel Prize in 1991 or something. These traps are tabletop experimental setups where you can actually trap ions, single ion, and work out its properties. It is an interesting physical system, and it is very, somewhat very interesting that this ion trap and this gravitational wave has the same dynamics. They have the same equations of motion. Therefore, you can make a correspondence between them, and working out the symmetries of one of them will give you the symmetries of the other. So they are very, very, somehow very much related, so to say. And if you see this correspondence, then it is a nice, I believe it is a nice somehow, if you can work out this relationship, then I believe it is a nice piece of theoretical work, let's say.
Thank you for
okay. So sorry, maybe it is a bit more complicated, a lot of things, but I hope that everybody actually at least understand the main idea how we do. I mean, in this.
Yeah, I think the organization or the development was fairly clear. So thank you very much for your talk.
Okay, I would like to thank to everybody for this invitation. Thank you very much.
And thank you all for the participation and not leaving until the end.
So by the way, I have a question. It's at some point you have shown a remark involving the virial theorem.
Yes.
Can you comment briefly about this?
Yes. I mean, now you see that the virial theorem is actually something that, okay, for a harmonic oscillator, right? The virial theorem here, I would like to tell you. Okay, so the virial theorem is, what does it do? Actually, it gives a relation between the total kinetic energy of the system and the Hamiltonian, right? I mean, physically, that is what we know for the virial theorem. And here you see for a harmonic oscillator, let's say, not Pais-Uhlenbeck oscillator, which is a higher dimensional theory. So what is your Hamiltonian or Lagrangian? It is, let's say Lagrangian is 1/2 dx over dt, t is the time, right? Squared minus 1/2 k is the Hooke constant, x squared. So that means your Lagrangian is actually a function of x. It's a quadratic function of x, right? So therefore, if you scale your Lagrangian, like x goes to lambda times x, your Lagrangian will be scaled as Lagrangian goes to lambda square times Lagrangian, right? So this is a kind of a symmetry. It is a scaling symmetry. If you would like to derive a conserved quantity for it, it will be exactly like this. So in the form of, it will be an integral charge, okay? From this symmetry, either it is relativistic or, okay, non-relativistic, let's say. If you would like to derive a conserved charge for a scaling symmetry, it will be an integral charge. So some part of the charge in the phase space will be given by an integral, okay? And you can integrate this charge, and you can actually, for a period, for instance, and this charge will give you nothing new but the virial theorem for a harmonic oscillator. It will give you that the average of a kinetic energy for the harmonic oscillator for a period will be, I think, 2 times. This 2 is the, it is the because your Hamiltonian or Lagrangian is a homogeneous function of x of 2, right? I mean, this is x squared. Therefore, it will give you that your kinetic energy will be 2 times, right? 2 times the Hamiltonian, or no, Hamiltonian will be 2 times the kinetic energy or something like this. So this is really, the charge is nothing, it's not a new charge, but it gives you the virial theorem if you integrate for a 1 period here. So that is actually related, right? That is why I tell that. So the scaling symmetry of the gravitational wave gives you always, in that case, a kind of a real theorem for the non-relativistic system. It will not give you something, a genuine conserved quantity, but it will give a physical property of the system, which is the real theorem for the system. That is what I would like to tell. So it comes from scaling, and this homothetic charge or homothetic symmetry is really a scaling here. You can see Here, this is the homothetic charge, and the action of the new derivative of this homothetic vector field on the space-time or a manifold. I'm unlike the word manifold. It will give you 2 times the manifold itself, and this is exactly the homothetic. So this is a scaling. So the action of the vector field gives you it is actually a scaling. So right. So it is a constant conformal factor. And if this action of the vector field actually scales or Lagrangian up to a constant, so it just multiplies it. So therefore, it doesn't leave invariant, but it's your Lagrangian, but the equations of motion are invariant, and it gives you a scaling charge, which yields the Villiers theorem. Okay, that is
okay. Thanks. Thanks.
Mm-hmm. Thank you.
Okay, maybe we can say goodbye, and we will meet the next talk. Some already left. Okay.
Okay, sorry for it is a bit long.
No. Thank you so much.
Thank you very much.
Thank you.
Mahmut. And it was great to see you again. I hope you have been doing well.
Well, I'm trying to survive. But it's okay.
Okay. I see. Without need of astrology or anything else, I guess.
No, I need astrology, definitely. I think.
Okay.
Survive.
Okay.
So,
Okay. See you then. Thank
see
you
you
very
then.
much.
Have a good day for everyone here.
Have a good day. See you.
See you.